Hello there, it's me again. I'm going to bring you through the third case study third one, which will be the last one. So far, you have looked at constant mass, F equal to ma, which I think about 80% of your questions will be. 80%. About 15%, you will deal with changes in mass. We shoot some water, we blow some air, turn on some fire extinguisher. Actually, this one got a lot when you think about it. Conveyor belt, sand coming out. Have you done those past year questions? Please go do them. All right. And now we're going to look at the third one where nobody is constant. GG. Otherwise undefined. Nothing is constant, which is just life, right? Nothing is constant in life. All right. Anyway, this one is otherwise undefined or both M and V not constant. I would say for A levels, this is not really part of your syllabus. It's just that occasionally they can throw you some strange looking graph and you go like, Nani, why is your graph like that? Okay, then you have to interpret in context, okay? So before I talk about that, here, I'm just going to say that technically it's not really in your syllabus, and to do what you actually need to do is using the chain rule. Because remember, it was D, dt, mv. So what do? You keep m constant, you differentiate v, plus you keep v constant, you differentiate m. Sounds familiar? Chain rule or your product rule of your calculus. Okay, so if you don't know this, I would say this is not in syllabus. But what is in your syllabus and what are the strange graph? Okay, before we look at the strange graph, I need to story you about impulse first. So let's go. Okay, so we are going to look at impulse and impulsive force from the root relationship. So not F equal to MA, not F equal to MdV, I mean V dm dt. We're going to start with F is equal to rate of change of displacement. Okay, so rate of change of momentum. So I record too many videos one go. Brain also a bit mushy. Rate of change of momentum. So rate of change of momentum here, it could be, if you written in word format, right, and assuming that the rate is somewhat constant, we can put this as change in momentum divided by the change in time. Okay, so we can write delta P over delta T. Okay, so let's say you have an object, all right, and then maybe you have a ball, lack of a better description, maybe it was traveling with a speed u, you give it a nice smack on the backside, give it a nice hit, okay, and now the ball is traveling at a faster velocity v. So how do you find the change in momentum? Well, you're going to go mv, or rather, maybe I'll write it out in another step for you first. We'll go with force as final momentum minus initial momentum. So the difference between initial and final. So in this case, they are both pointing to the same direction. So it's, no need to worry too much. But if there's a rebound case, which we will look at later in the papers, you put negative sign, my friend. Okay, so if it's a rebound case, then no. But in this case, we're going to stick to the vanilla case first. mv minus mu over t. All right, and then maybe you have seen this before. Maybe your teacher factorized the m and then v minus u over t is acceleration. Also can. But I want to point out something to you first. Number one, this change in momentum, this delta p, hang on, where is my over t here? Divide by delta t, okay? Okay. This change in momentum is called a different name as well. It is also called impulse. Okay, so impulse, I'll write here first. Impulse is change in momentum. Teacher, why like that? Well, we just want to have a different physical quantity. Okay, because sometimes when we want to apply a force, the contact time is the same. Okay, so how long my hand is in contact with the ball could be the same. But if I want the ball to change more velocity, the change in momentum is more. But impulse, in a nutshell, is change in momentum. Okay, sometimes they will use the symbol J. Okay, and the unit here, because it's change in momentum, the unit will be kg ms -1. Okay, then teacher, impulsive force leh? Impulsive force is just force lah. Generally, we use impulsive force. Maybe this F is impulsive force. Generally, this is used or considered as impulsive force if this T is small or fast. So maybe you use a racket and hit a tennis ball very fast. Okay, so it's not like you consistently push a box. Okay, so normally this is small, and normally it is involved in some kind of hitting or collision. Okay, so that's impulsive force. All right, but one more thing I want to highlight from here is that whenever you study physics and you see this dp dt, rate of change, while most of the time you will not be given a function to differentiate anything, but you have to understand that whenever f is dp dt is written like this, what it implies here is to find force, we will look at the gradient of your PT graph. Okay, so the very least you should know this. From F is dp dt, F is the gradient of your PT graph. And also sometimes I can move things around, you know. So if I move things around, if I differentiate, okay, let's see. If P and F, no space, so I borrow number 9 a bit. Okay, so if P and F, okay, I differentiate this one, d dt, and I get force. Then when I got stun or reverse back, what do? You smart people there. Teacher, you integrate lor. Then I know we did this before in displacement, velocity, acceleration. Correct. So this one is integrate with respect to t. But if you don't know calculus, then what this means down here is if f is the gradient of PT graph, then in the reverse world, p, which is the gradient, P, which is the impulse or change in momentum. Okay, change in momentum will be equal to integration of f dt. Or in other words, this is area of the ft graph. Okay, so when you consider Newton's second law, right, there are a lot of variation that the question can branch out. Okay, we have looked through the more common variation, and now normally sometimes in certain objectives they will give you a graph. Okay, so whether it's PT or FT, you should know how to get one from the other. Okay, so in summary, because from Newton's second law, F is dp dt. So if you have a PT graph, something like this. Okay, so the graph looks like this, or fun. So your gradient here, gradient at this point, that means at this given time, or let's say 10 seconds, the force, the gradient is equal to the force applied on the object at 10 seconds. Okay, and if let's say you are given a force against time graph, maybe I apply some force here and then I don't apply some force, this area is equal to change in momentum or impulse. Okay, so there's a two-way relationship. That's why we care about change in momentum, and we want to give it a new name called impulse because it's area under the FT graph. Okay, so this one, in a nutshell, right, when you talk about impulse, I will rearrange these notes a bit later. We are talking about change in momentum over time. So let's say I rewrite as del P over del T. All right. So when I do so, what I'm looking for is mv minus mu. Final momentum minus initial momentum here. All right. So from here, normally the change in momentum itself is called an impulse. Symbol sometimes given is J, but I'm sticking to delta P. Okay. Change in momentum. Unit will be kg meter per second. So because of this relationship, right, F is dp dt. So I know F is the gradient of a PT graph, momentum time graph, and impulse is the area of a force time graph. All right. Okay, So I think if this part is okay, we're going to jump straight to some questions. You run out of space, so did I. So I tell you what, this part, if you're writing on your own printed out notes, okay, this part we cancel lah. Teacher, the free fall leh? Don't worry, don't worry. Miss Ellie will talk about this in 3.2, but I think you already know this already. What? The weight of an object in free fall is mg. So just gonna. Okay, all right. So you can put this here before we jump into some example. I also forgotten to mention something that you also probably already know, but just a statement here. 1 Newton here is the SI unit. Okay, so the SI unit for force, on the right here, force. SI unit is Newton. You can use kg meter per second, all right? But also at the same time, this is a vector. Okay, so let me bring up the whole family for you. F is equal to dp dt. So F vector, momentum also vector. Then impulse also vector. So impulse is also a vector quantity. Okay, so whenever you encounter a physical quantity, right, it's just good habit to ask yourself, is this a vector, is it a scalar? Okay, so most of the times when people who are fluent in physics or used to physics, we instinctively already know it's a vector, then we just forgot to tell you. Sorry, okay. So force is a vector, momentum is a vector, impulse is a vector. Direction matters. All right, direction matters. Okay, so both are vectors, and I think we can continue to do some examples now. Here, about this kind of graphs. Okay, so here is a graph, right? It says here, this question is on page 16. Okay, it says here that the resultant force of 10 Newton acts on a body for a time 2 seconds. Okay, sure. My dude, this is F. Which graph could show the variation with time t, the momentum p of the body? Well, let's see. Force is rate of change of momentum. So this happens to be gradient of your PT graph. So I guess which gradient of PT graph is 10? Okay, 10 Newton. Let's see. Let's check out the first line, A. A dropped to about 10. So this gradient for A, dp dt is equal to 20 to 10. You can put negative 10 if you want. Okay, so we just want the magnitude of the force. But just to be good, I'm treating this as absolute. Okay, so 20 to 10 is a drop by negative 10. Okay, and then the time taken here is 2 seconds. So this is negative 5 Newton. Nope. Okay, so not A. Let's try B. Okay, let's try B. B is 20 to 0. Negative 20. Okay, so the whole drop is 20. And then divide by 2. Yay, negative 10 Newton. So the answer is probably B. Okay, and you can probably tell that the force of A is 5 Newton, negative in the negative direction. Okay, and the force of C is also 5 Newton. 10 divided by 2 is 5 Newton. And this one is 2.5 Newton. And the reason why they all will have negative sign is simply because to decrease the momentum of an object, let's say you have a trolley moving at this direction, V, don't care lah whether the V is 20, whether the momentum is 20, 15, 10 or 5, moving in this direction. This is the direction of positive momentum. To decrease momentum, F have to be in the opposite direction. So this is the change in momentum or the impulse, because force is also in this direction. Because the change in momentum and the force is in this direction, that's why the momentum, mv, decreases. That's why you see all this graph, the momentum is decreasing from 20 or from 10, decrease. That's why A, B, C, D shows a decrease in momentum. All right, so the change in momentum is in the opposite direction. They're taking the forward direction as positive. That's why there is a negative sign there. Whenever you see a negative sign and you don't know why it's there, it's probably related to vector. But if you can't reason it out, ask someone, talk about it, okay? Because to ignore a negative sign, it's not a very positive thing. All right, let's look at a different graph. This is on page 17, or winter 14 paper 13. Wow, this slopey graph. Anyway, a body experiences a varying resultant force. Wow, this resultant force keeps changing. Yes, it keeps changing. Magnitude. So you can see the gradient keeps changing. It also keeps changing direction because there are certain places where the gradient is positive. And then there are certain places like this point here, although it's not marked, where the gradient is negative. Okay, so this varying resultant force, in case Miss Lee sets an objective question, okay, a statement here is, this one change in magnitude. How do we know there's a change in magnitude? Because the gradient changes. I mean, duh. Okay. And there is also a change in direction because some parts the gradient is positive, some parts the gradient is negative. So this part here, positive gradient. It's like toying with the feelings of the object lah. Here is negative gradient. So you have an object like that. Let's say sometimes you will pull it in this direction. Sometimes you'll pull it in the opposite direction just because. Okay, so your gradient changes sign, plus, minus. Okay, so that's how we know the force changes. All right, so the question is pretty straightforward. It says, at which point does the resultant force have the largest value? So largest value here means largest magnitude, which means we are looking at the steepest point. So where is the steepest point? A, the gradient looks like 0. Gradient 0, 4, 0, sadness. F also looks like a turning point. So gradient 0, force 0, depression. The only thing you have now is B and D. Okay, and I think comparatively, just judging by eye, you will see that B is a lot more steeper compared to D. But if you cannot, during the exam, you can always draw a line. Okay, just like in bad relationships, you can always draw a boundary or a line. And hopefully that line is straight. Okay, let me see. Let me try. So let me draw a line to indicate the tangent at point D, something like this. And I will draw another line to indicate the tangent at point B. Let me draw this properly. Hang on. I wish for a ruler that I do not have. OneNote doesn't have a ruler. Okay lah, something like that lah. Cukup lah, boleh lah, can lah. The Malaysian way of saying this is good enough. Close enough. Obama face. So you can see that this purple line is less steep compared to the blue line. All right, learn to draw tangent line if you can't judge by eye that B is steeper than D. So essentially what they're asking for is which point is the curve having the steepest gradient. Okay, so that will be point B. I mean, upon the point, amongst the point A, B, C, D lah. So what I could do is I could make the question a bit harder. I could ask you like, oh, amongst this point, which point the force is 0? At which points are the forces in opposite direction? So if you understand very well that the gradient of a momentum time graph, gradient of this is equal to force, then it's just reading the gradient at different points, which you should be very pro already because you did the kinematics chapter. All right. Here's another example. It's a bit more recent from May, June 20, Summer 20, Paper 1-2. You can find it in your handouts in page 35. So here this example, it says a resultant force is slowly increased. Okay lah, you already watched me do 2 examples. You pause the video. I pause the video. Pause the video and decide which one is the variation of your momentum time graph? Okay. Resultant force slowly increase. Pause the video. Think now. Okay, I hope you have an answer in your brain. Okay, let's see if your brain is putting the concepts together properly. All right, first things first. Force and relation with this. Well, if you always like confusion, I'll just write force is the gradient of momentum time graph. Okay, so if the force is slowly increasing, it means the gradient must be slowly increasing. Okay, slowly increasing in normal people term, it's just the graph is getting steeper. So the graph that is not getting steeper, you can throw away. Like, for example, this one, the gradient is constant. Gradient constant, force constant, and buzzer sound, okay? What about C? You look at C, the momentum, the gradient is getting less and less steep. So gradient is decreasing. Force is decreasing. Wrong. Teacher, A leh? Momentum increase. Momentum increase, but you look at the shape. Here is steeper than here. Right? So here, this one also, gradient decreasing, F decreasing. Oh, so we only look at gradient. Yes, we do not look at the absolute value. So the answer is B, because if you check out this part here looks very flat, whereas this part here looks steeper. So this one, gradient increase, force increase. But miss, why the force increase but the momentum decrease? Why the force increase but momentum decrease? Let me explain. Okay. Okay, I give you numbers. Let's say I have a trolley. Trolley, I make my life easy. 1 kg. Okay. And then the trolley is moving in this direction at, let's say, 10 meters per second. Okay. So at t equal to 0, maybe I apply a force of 1 Newton. But be aware, this force have to decrease the momentum of the trolley. How do you decrease the momentum of something that is moving? You slow it down. How do you slow down this trolley? You want to decrease its momentum? You say, slow down, bro, slow down. You apply a force this way, 1 Newton. Then after that, maybe when t equal to 2, then let's say this is t is equal to 2 seconds. Cannot see. Let's means the t equal to 2 seconds. Then this one, maybe, I don't know. We need some more information. But let's say the force decreased now. Let's say now it's a smaller v. Then you will apply a larger force, 2 Newton. So this means the velocity will slow down faster and faster. That's why the momentum will decrease more and more. With greater and greater time. So this shows a decrease in momentum. And as you apply more force, right here, as F increase, change in momentum, or the rate of change, momentum changes, or specifically decreases faster. That's why we have a rate of change of momentum. That's why we care about these things, okay? So in other words, we check using gradient and don't let them fool you. Just look at the shape of the graph, not the absolute value. All right. Okay, a few more examples to round off this recording. And also your understanding of Newton's second law. Pretty important law here. So this one is on page 16, MJ14 paper 1-2. Okay. So a lot of times, you see, the question try to trap you. Okay, it says here a resultant force causes a body to accelerate. What is equal to the resultant force? I tell you, a lot of students, they want to jump on the fact that, force causes body to accelerate. So they like to do, it's the acceleration of the body per unit mass. No. Whenever you talk about statement, this is wrong. This is not a universal statement. Not universal statement of your Newton's second law. Okay? You don't have information about the body. Maybe the body is slowly leaking out its mass. Maybe the body is like a squid and it's like spraying ink out. You don't know. Basically, you don't know. Not a universal statement. The universal statement is this. Force is rate of change of momentum or change in momentum per unit time. Only this is the legit one. Hashtag formal. Hashtag legit. Use this. Okay, so you just go for a change in momentum per unit time. Ta-da! Okay, don't let them trap you because they already know that you are very familiar with F is ma. Please understand that Newton's second law is only change in momentum per unit time or rate of change of momentum. Okay, this is the formal, this is the legit one. This is a special case where m constant. This one. So in this case, this is wrong. All right. Okay, let's look at 9. 9, we're going to apply a calculation based on our understanding of what impulse is. Okay, so on 9, we have a ship of mass this much. It's approaching a harbor with a speed of this much. Okay, bon. By using reverse thrust, it can maintain a constant total stopping force. Constant stopping force of 920 Newton. How long? How long will it take to stop? Okay, to do these questions, you may be thinking, Miss, you see, this how long is T? Do I stuva? Well, you could stuva because you're approaching the harbor is 16.4 meter per second. And you want to stop right now. Thank you very much. So this is 0 meter per second. If you know, you know. You don't have the rest. I mean, you are looking for time, but you don't know the distance traveled. So this one, we don't have, no have. Teacher, I know acceleration can find what? I got M, I got F. Oh, snap. You are so smart. So we can find acceleration first. We're going to use F is equal to MA. So 920,000 is equal to 8.4 times 10 to the power of 7, 8. So a bit like a sideways to kinematics. Yes, they're all related, child. They're all related. Everything is related. Legitimately. Okay. So this acceleration is 0.011. I will take 2SF. Okay. Don't worry about it, even if it's pretty small, because, you know, it's a very massive ship lah, okay? The inertia is very big, so the acceleration is small. So now we can use stuva, okay? So I will use the equation with no S. That equation would be no S. V is U plus AT. So 0 is equal to 16.4 plus, I forgot. Were you thinking about this just now? This must be negative. If you're wondering why negative, then think about your boat. Okay, I'm going to draw a boat now that will look like a... Miss Lee cannot draw, okay? Miss Lee can do many things. Drawing is not one of them. Okay, so if the boat is traveling, this is harbor. This is the harbor here. Harbor. So if the boat is traveling here at 16.4 meter per second, if you want to slow down the boat, the stopping force must be in this direction. This is the force. This means this is also the same direction as acceleration. So if 16.4 you give positive, then acceleration must be negative. So I put a negative here, okay? Also, my time cannot be negative. That should be a good clue for you that something is off. So from here, I can find T. I'll take 16.4, divide by the answer just now, or 0.01. I'll get 1497. Don't panic first. This is second. Need to convert. So this is out. This is out. Need to convert to minute. Okay, I divide by 60. This is 24.96 minute. So 25 minute long. Okay, don't panic first. Teacher, no answer. Check the units. Okay. All right. So some of you might be thinking, teacher, isn't this like a Newton's second law question? Maybe, but I can use impulse to answer the question. So this is a two-step process. I find acceleration, and then I use kinematics or Stuva to find my time. Alternative is I could take change in momentum. So, or I can use F is equal to change in momentum over change in time. Okay, I know the stopping force. The stopping force here is 920,000. We are looking for the change in momentum. Do we have the mass? We can take mv minus mu. But this one is 0 because we need to stop the object. Okay? And then this one you will divide by t. So I guess if I want to find t, okay, and then again, this is directional. So if you don't want to have a negative sign here, there should be a negative sign here because the direction of F is negative compared to the direction of U. This is U. Okay, so both negative, both sides, so they cancel out. At any rate, it's objective, so magnitude is good enough. So T here would be mu. The mass is 8.4 times 10 to the power of 7. The speed was 16.4 divided by the stopping force, 920,000. And if I put this in my beautiful calculator, 920,000, I will get 1497 seconds again. So we could also solve this using impulse or change in momentum over time, which is your force. So remember, force is change in momentum over time. It's not always ma. Actually, in this case, it's still ma because the mass of your boat is constant. All right. So 2 ways to do the question. All right. So it's up to you. And with this is the end of this video. I'll see you in the next one. Bye.